Dear learners, welcome to this session of marketing research. In our previous session, we discussed the various steps in hypothesis testing for a single population mean. We also discussed the important assumptions that need to be taken into account for applying Z statistics, such as the randomness of the selected sample. That means every member of the population should have an equal opportunity to be selected. Sample data should be normally distributed with a known population standard deviation. A large sample size and ideally a sample larger than 30. This is because of the central limit theorem, which assures that when sample size increases, the distribution of the sample mean tends towards a normal distribution regardless of the original population distribution. We also calculated the Z statistics for a single population mean with the help of a formula and applied the concept of the critical value approach to identify acceptance and rejection regions for the null hypothesis. If the computed value of the test statistic fall in the acceptance region, the null hypothesis is accepted, otherwise it is rejected. In this session, we will further extend the discussion on the steps of hypothesis testing for comparing the means of two different populations. The learning outcomes of this session are: explain how to calculate Z statistic for the difference between two population means, describe the steps of hypothesis testing for the difference between two population means with Z statistics, explain how to calculate T statistic for the difference between two population means, discuss the steps of hypothesis testing for the difference between two population means with Z statistics, and make informed decisions based on population mean comparisons. So in the earlier session, we discussed hypothesis testing for single populations. However, many a time the decision maker is interested in knowing whether two related populations are different from each other in respect of any parameter of the population. For example, a marketing manager might want to determine if a point of purchase display impacts average retail sales. In such scenario, the focus is not on the individual population means, but rather the significance of the difference. In this session, we will examine testing for differences between two means. In order to achieve this, we have to take one sample from each of the populations independent of the other, and we want to test the difference between the two population means based on the evidence produced by the two samples. In other words, we will focus on statistical inference in situations involving two or more populations. As we have discussed that the Z statistics is used as a tool for statistical inference for large samples and the T statistics is used for small samples. We will be discussing Z statistics and T statistics for hypothesis testing of two populations in this session. Let us discuss the hypothesis testing for the difference between two population means by taking an example. The case situation is that a marketing manager wants to know if point of purchase display helps in increasing the sales of his product. Unless there is strong evidence to the contrary, he is likely to believe that such displays do not affect sales. He picks up 70 retail shops where there is no display and finds that the weekly sales in these shops has a mean of rupees 6,000 and a standard deviation of rupees 1,004. Similarly, he picks up a second sample of 36 retail shops with display at point of purchase and finds that the weekly sales in these shops has mean of rupees 6,500 and a standard deviation of rupees 1,200. What should he conclude at a significance level of 5%? So this is a situation. Now the decision problem of given scenario can be analyzed using a two sample independent t-test to determine if there is a significant difference in weekly sales between retail shops with and without displays. In step 1, we had to set null and alternative hypothesis for the given situation. So the null hypothesis can be stated as there is no significant difference in the mean weekly sales between retail shops with and without point of purchase display, and this can be represented as 0 such that mu1 is equal to mu2. Here we have used subscript 1 to denote the first population, that means without display, and subscript 2 for the second population, that means retail stores with displays. The null hypothesis in this case reflects the marketing manager's initial assumption regarding the impact of point of purchase display on sales. As we have seen earlier, unless and until the sample evidence strongly differs, the marketing manager is likely to comfortable maintain the current approach, which means he would like to maintain the status quo. And the alternative hypothesis for this situation can be stated as there is a significant difference in the mean weekly sales between shops with and without displays, and it can be represented as H sub 1 such that mu1 is not equal to mu2. This formulation of alternative hypothesis suggests that it is a case of two-tailed test. This is because it simply states that the average weekly sales for stores with displays and those without displays are not the same. It does not specify whether sales are higher or lower with displays. Step 2, we have to determine the appropriate statistical test. So, setting the hypothesis, now we have to select the statistical tools. As the given sample size of 36 retail stores with displays and 70 without displays indicates the samples are greater than 30. So, we can use the Z test as the for sample mean is also given. So, for hypothesis testing, we can use Z statistics, and the formula can be written as Z is equal to bracket in x1 bar minus x2 bar minus bracket mu1 minus mu2 divided by under root s1 square by n1 plus s2 square by n2, where the x1 denotes the sample size of group sampling 1 or group 1, and the mu1 is the population mean of group 1. Similarly, the sample variance s1 square is for the sample 1 or group 1, and similarly for group 2 sample size is n2, sample mean is x bar 2, population mean is mu2, and sample variance is s2 square. The third step is the set the level of significance, and we generally set limit alpha as 0.05. Step 4 is we have to define the critical regions in terms of test statistic. So here we have to establish the decision rule, that means deciding a critical region. As we discussed, hypothesis testing evaluates whether the observed data provides sufficient evidence to reject a pre-established null hypothesis. The critical area under a normal distribution curve helps to decide whether to accept or reject the null hypothesis. To make a decision, researchers need to define a critical value that separates the area under the normal distribution curve into the acceptance and rejection regions. If the computed value of the test statistic falls in the acceptance region, the null hypothesis is accepted, otherwise it is rejected. So, acceptance and rejection regions for two-tailed test at 5% level of significance is shown in figure 1. The acceptance region covers 95% of the area, and the rejection regions covers the remaining 5% of the area at the two ends of the distribution. So, the critical Z values can be obtained from normal table 1 as plus minus 1.96. It means if the computed test statistics Z is between plus minus 1.96, the decision is to accept the null hypothesis, and if the computed test statistic Z is outside plus minus 1.96, the decision is to reject the null hypothesis and accept the alternative hypothesis. Step 5 is the collect data is already provided in the given situation. Sample size is 70 for group 1, the mean is 6000 for group 1, standard deviation is rupees 1004 for group 1, and for group 2 the sample size is 36, mean x2 bar is 6500, and standard deviation sigma 2 is 1200. We can substitute the sample variance S1 for sigma 1 population variance and the S2 for sigma 2, as both the N1 and N2 sample size are larger than 30. Then next step is analyze the data. Here we have to put these values in a formula. So we can put x1 bar as 6000, x2 bar as 6500, and the mean the difference mu1 minus mu2 are negligible. So we can replace the 0 in place of mu1 minus mu2, and then we can substitute variance S1 square as 1004 square and N1 70, S2 square is 1200 and N2 is 36. So by putting this value in this formula, we can get the value as minus 2.14. Now we have to arrive at a statistical conclusion. At 95% confidence level, the critical value obtained from the Z distribution table is plus minus 1.96. The observed value of Z is calculated as minus 2.14, which is lower than the tabulated value of minus 1.96 and falls in the rejection region. Hence, the statistical conclusion is to reject the null hypothesis and accept the alternative hypothesis. Now, in terms of the marketing research problem, it can be concluded that there is a significant difference in the mean weekly sales between shops with and without displays. So, the null hypothesis that is stated as there is no significant difference in the mean weekly sales between shops with and without display is rejected, as there was sufficient evidence to support a change, and an alternative hypothesis was accepted that is stated as there is a significant difference in the mean weekly sales between shops with and without display. These findings offer valuable insights for optimizing sales strategies. Here are some professional managerial decisions to consider. One is strategic display implementation. That means we can select standardization or customization based on the analysis of display effectiveness, for example, type and placement, etc. A standardized display format can be implemented across all shops. Alternatively, customization based on shop size and product category may be more appropriate. Second strategy can be optimizing display effectiveness. For this, the targeted research can be conducted. For further research to isolate the specific elements of the displays driving the sales increase, investigate factors like display type, floor stand, shelf display, etc., product placement strategies, and promotional messaging effectiveness. Then we can also analyze the return on investment. So for this, the cost benefit evaluation can be done. Calculate the cost of implementing and maintaining displays compared to the demonstrably increased sales they generate. This return on investment analysis will determine the long-term financial viability of a company-wide display program. Other can be, we can go for the pilot program for cautious implementation. In case of the phased rollout, if a full-scale implementation seems strategically risky, consider pilot program in a selected group of shops. This allows for testing different display strategies and measuring their impact in a controlled environment before a larger rollout. So now let us discuss the same example of the decision problem faced by the marketing manager with a smaller sample size, where he wants to know if the point of purchase display helps in increasing sales. Now he picks up 12 retail shops with no displays and finds that the weekly sales in these shops has a mean of rupees 6,000 and a standard deviation of rupees 1,004. Similarly, he picks up a second sample of 10 retail shops with displays at the point of purchase and finds that the weekly sales in these shops has a mean of rupees 6,500 and a standard deviation of rupees 1,200. What should he conclude at a significance level of 5%? Here, say it decision situation 2. You can observe that only changes are in the sample size of retail stores without display and with display. The sample size is 12 retail shops with no display and 10 retail shops with display. The sample mean and standard deviation values are the same in the earlier discussed example 1. Now let us discuss the hypothesis testing steps for this decision problem. So step 1 is set null and alternative hypothesis. So here null and alternative hypothesis will remain same as earlier. That means There is no significant difference in the mean weekly sales between retail shops with and without point of purchase displays is the null hypothesis, and it is written as H sub O such that mu1 is equal to mu2. And the alternative hypothesis is there is a significant difference in the mean weekly sales between shops with and without display, and it is represented as H sub 1 such that mu1 is not equal to mu2, and it is a case of two-tailed test. Now, determine the appropriate statistical test. In this case, the sample statistics will be changed because we have a smaller sample size. 12 retail stores without display and 10 with display, which is less than 30. Recall that in the first decision situation, we selected Z statistics as the given sample size of 36 retail stores with display and 70 without displays was greater than 30. As we know, Z statistics is applicable for large samples when the population standard deviation is known, and when it is unknown, the sample standard deviation can be used in place of the population standard deviation. However, in this case, when the sample size is small, less than 30, and the population standard deviation is unknown, the T statistics will be an appropriate statistic to test the hypothesis for the difference between two population means. The T statistics is also based on the assumption that characteristics being studied is normally distributed for both population. The formula for T statistics under the assumptions of equal variance is given as equal to T is equal to in bracket x1 bar minus x2 bar minus in bracket mu1 minus mu2 divided by sigma under root 1 by n1 plus 1 by n2. Here the sigma standard deviation can be replaced by the pooled standard deviation represented by S pooled, and it is given as under root S1 square in bracket n1 minus n1 plus S2 square in bracket n2 minus n1 divided by n1 plus n2 minus 1. Here the subscript 1 denotes for group 1 and subscript 2 denotes for group 2. The third step is set the level of significance. We already stated that the level of significance is given as 0.05. Now define the critical region. So we have to define a critical value that separates the acceptance and rejection regions. If the computed value of the test statistics falls in the acceptance region, the null hypothesis is accepted, otherwise it is rejected. At the given level of significance, alpha equal to 0.05, for two-tailed it is 0.025, and the n1 plus n2 minus 1 degree of freedom, that means 12 plus 10 minus 2 is equal to 20. The tabular t value from table 1 is plus minus 2.086. It means if the computed test statistic t is between plus minus 2.086, the decision is to accept the null hypothesis, and if the computed test statistics is outside plus minus 2.086, the decision is to reject the null hypothesis and accept the alternative hypothesis. Step 5, collect the sample data. So sample data is already given. Sample for group 1, sample size is 12, mean is 6000, standard deviation is 1004. For group 2, sample size is 10, mean is 6500, standard deviation is 1200. Now we have to substitute this value in the formula given for T statistics for analyzing the data. So by substituting this value, we calculate the standard deviation sigma as S pooled by putting this value N1 12, the S1 1004, N2 is 10, and S2 variance is 1200. So by putting all this value, we get S pooled as 1096, and when we put this value in T formula, so we get 6000 minus 6500, and the mu1 minus mu2 difference is negligible, so it is replaced by 0, and the sigma pooled, the value of sigma pooled is 1096.54. So by putting this value, we get T as minus 0.456. So now we can reach at a statistical conclusion, and we can say that at 95% confidence level and 20 degree of freedom, the critical value obtained from the T distribution is plus minus 2.086. The observed value of T is calculated as minus 0.456, which is higher than the tabulated value and falls in the acceptance region. Hence, the statistical conclusion is to accept the null hypothesis and reject the alternative hypothesis. On the basis of this hypothesis testing, it can be concluded that there is no significant difference in mean weekly sales between shops with and without display. So the null hypothesis is accepted here, and there was no strong evidence to support a change, and alternative hypothesis was rejected here. The decision for the manager decisions can be maintain current display strategy because the test showed no significant difference in sales between shops with and without display. There is no evidence to suggest display are driving sales. You can decide to maintain the current display strategy regardless of whether shops use display or not. Maintaining the current strategy avoids unnecessary costs associated with display creation, maintenance and potential rollout across all shops. However, it should be considered that are there potential benefits beyond direct sales increase? Display might enhance brand awareness or influence customer behavior within the store. And second is the lack of overall impact of a function of the test limitations. For example, sample size or product category might not have been fully accepted. As we have seen, the same null hypothesis that is accepted here was rejected in earlier example of a first decision situation where the sample size was larger. Also, due to the large sample size, we could have selected the Z statistics instead of the present case of the T statistics. Second decision, we can go investigate display effectiveness further. No significant difference does not necessarily mean displays are ineffective. They might be beneficial in specific context, and further investigation can help identify this context to inform a more targeted future strategy related to product category, shop location, display design, and so on. So with this, we can conclude the session. In this session, we explained how to calculate Z statistics for the difference between two population means, describe the steps of hypothesis testing for difference between two population means with Z statistics. We explained how to calculate T statistics for the difference between two population means. We discussed the steps of hypothesis testing for the difference between two population means with Z statistics, and we applied the concept learned in real life marketing decision problem. So with this, now let us check your progress by attempting these questions. Question 1 is, when comparing the means of two populations, what is the null hypothesis typically represent? Option A, the observed difference between the sample mean is statistically significant. B, there is a strong correlation between the two variables being compared. C, there is no difference between the population means. And D, the sample size is too small for an accurate comparison. Question 2, which of the following is not a common type of alternative hypothesis when comparing means? Option A, the mean of population 1 is greater than the mean of population 2. B, the means of the two populations are different, directional, two-tailed. Option C, there is a statistically significant difference between the means, non-directional. And D, the mean of population 1 is exactly twice the mean of population 2. Question 3, which statistical test is most appropriate for comparing the means of two independent samples if the population variance are unknown and assumed to be unequal? Option A, one sample t-test. B, two proportion z-test. C, pooled t-test. D, pair t-test. Question 4, what does the critical area in hypothesis testing represents? Option A, the area under the normal distribution curve where the null hypothesis is true. B, the area under the normal distribution curve where the null hypothesis is likely to be false. C, the entire area under the normal distribution curve. And D, it depends on the specific test it is used. The question 5, how is the critical area defined in hypothesis testing? Option A, by a single specific value on the x-axis of the normal distribution. B, by a predetermined significance level alpha. C, it is automatically generated by the software used by analysis. And D, it doesn't require any definition, it's inherent in the data. So with this, we end the session. Thank you. Happy learning.